Good afternoon, everyone. It's quite smaller crowd today. I guess people start going on Thanksgiving vacation. I know Scott is very popular among students. It's one of the most popular courses, right? 140, 150 students. Just an announcement. This is we have one more seminar, December 2nd. Alfred Spector from 2 Sigma, talking about the data science in finance. You all here, you know, this is a seminar for the Institute for Applied Computational Science. We cover topics that related to data science, computation, and how it's related to the rest of the world. So today's talk is we're looking at computation with how we control robots and how efficient we can do that. Scott is going to talk in a bit, but let me first introduce Scott. It's a great pleasure to have one of our own people here, assistant professor. He did his master's and PhD at Amherst College, UMass. Then he went to MIT as a postdoc. He worked in 2 labs, the Robot Locomotive Lab and DARPA Robot Challenge.
Oh, yeah, it was the project was the
the project. Yeah, sorry. And now he's here at CIS since last year. He's an assistant professor and director of the Agile Robotics Lab. His research interest, if I got it right, is about using computation to optimize robot behavior. And today he's going to be talking about controlling multi-contact robot behavior within optimization.
Great.
Please help me welcome Scott.
Great, thank you. All right, I'm on, I guess I'm on, cool. So thanks everyone for coming. I know the holidays are coming up, so glad you're here. I apologize in advance if I'm slightly froggy or if I pass out in the middle of the talk. I'm sort of like recovering from this obnoxious virus. It's like the 3rd daycare-related virus I've gotten since my toddler started going to daycare. So yeah, today I'm going to talk about some of the work that we're doing in optimization, specifically using optimization as a tool to control physically complex robots. Okay. But what I'd like to do is start out with the simplest robot, right? Because I know that, or if I'm guessing correctly, many of you don't have direct experience with nonlinear control or any of these sort of ideas that our group works on regularly. So let's look at the simplest robot. Okay, so this is a pendulum. Now you might be thinking that's not a robot. Well, it can be a robot, right? So if I stick an actuator on the base of that pendulum, then now I have something that I can control, and so that's kind of like the simplest robot. You can think about this as a really trivial robot arm, right, that I can just move around. All right, so how do we begin? How do we begin answering questions about how to control a system like this? Well, you might remember some properties about, you know, how different physical quantities of pendula relate to, you know, their period and all that kind of stuff. That's not really what I'm interested in, although that's, you know, an important property. We can think about other things, though, more global properties of these systems. Like, for example, if I take this pendulum, I define a coordinate. I just say, OK, my angle from the vertical, I'm going to call theta. Right? Now I could draw this pretty picture. And maybe you've seen this picture before. This is called a phase portrait. All right. So on the x-axis is the angle. On the y-axis is the angular velocity. All right. So now I can draw these little arrows here, and that's going to somehow tell me what the flow of the dynamical system is over time. Okay? So this blue trajectory is actually what you saw when the slide transitioned. It's this behavior, right? So I start off at some state, which is going to be a point in this phase portrait. So I have some angle with 0 velocity. I let go. Gravity takes over. It starts to swing down, right? It accumulates a negative velocity, crosses the 0 position, goes back up, right? And then because we're assuming this is sort of an imperfect hinge here, it's going to dissipate energy over time, and it's eventually going to sort of converge to the origin. Okay? So that's a really nice sort of graphical way to understand dynamics. Now, unfortunately, we're not able to do this, and we get to systems much more complicated than a pendulum, just because the dimensionality is too big. So what do we do then? Well, I'm going to use this as an opportunity to introduce some notation that I'll use throughout the rest of the talk. So what do we do? Well, we write down equations, and then we operate on those equations. That's how we design controllers. So what do these equations mean? Well, I define some state of the system. Whenever you hear me say the word state, I mean something very specific. It's a vector that contains all the positions and velocities of all the degrees of freedom of the robot. Okay? we're going to have some input or action that we call U. And you could just think of this generically as torques that I can apply to some subset of these joints. All right? And then the equations of motion, maybe you even know the pendulum equations of motion off the top of your head. You've probably seen it before in the Physics 101 course. The details don't matter, but generally speaking, we write down the dynamics like this. We say that if I give you the state and I give you the input, there's some nonlinear relationship here. This has sines and cosines and things like this. And I can tell you how the state is going to change with respect to the state and input. All right. So that's the pendulum dynamics. Let's ask our first control question. What if I told you I wanted you to come up with a way to design torques, right, for our little actuator here, such that the robot becomes stable now in the vertical position, no longer down here? How did you do that? I'd love to hear from someone who's never written a controller in their life. Just think about intuitively how much you design this little function such that everything flips upside down. Any ideas? What about this one? I could just design some torque, right? It's going to look at the state, say, what is gravity going to do? Cancel that out, and then do the opposite, right? That's perfectly fine, right? I didn't tell you there's any kind of limitations on this motor or anything like that. I could just write that down. So now we can run our new pendulum with a controller acting on the shoulder. And what's going to happen? Well, this phase portrait's going to shift all around, right? All these arrows now point in slightly different directions. And what's happened now, I've started in the same state as before. Instead of going like this, now I go like this, okay? So the first idea I want you to have in your head as I'm talking today is that control is a way to reshape the phase portrait of a dynamical system. Okay? So there's many such ways to do that. And if I look at sort of the difference between here's my initial phase portrait and here's the one I've used control to change. See if I go between these two things. It's not the best visual, looks better on my computer monitor, but essentially what we're doing is we're sort of changing the y component of all these little vectors, right? And now we have a choice. How do we make that choice? How do we decide how we want to change the y component of these vectors? Is this the sort of least torque way to get the pendulum to the top, right? Do you think that this is the best way you could design a controller for this system? One that's going to do it by sort of minimizing effort? Probably not, right? Because when I'm down here, I'm generating huge amounts of torque to cancel gravity and also accelerate the thing really fast up to that position. Okay, so you're already starting to hear, in the way I'm speaking, that there's an underlying optimization problem that we could write down if I want to say, make sure I get to the vertical position while minimizing torque. Look, how about this system? Now, this is obviously slightly more complicated than the pendulum. Now we've got essentially two links fused together with an additional joint in the middle. So it's kind of like a double pendulum. With the additional constraint now that I only have one actuator, right? So I just have an actuator. If you think this is an arm, this is just my elbow. And now I want to ask the same question. How do I design a feedback controller for this elbow to stabilize the whole system at the vertical? Now this one I wouldn't expect you to come up with an answer, on the back of an envelope, right? Because it's not even clear, maybe to you looking at this, that you can somehow generate some sequence of torques here that's going to get the whole thing to stand up at the vertical, right? So we call a system like this underactuated, right? And in this case, it literally means that I've deleted an actuator from the joint space. But there's more sort of subtle types of underactuation, which I won't get into. But the idea here, though, is when you have an underactuated robot, I have to simultaneously exploit the passive and the passive dynamics and the actuation in order to achieve goals. Okay, so it's no longer simply a matter of choosing some actuated input that just wrangles the dynamics into whatever I want, right? It's, again, completely cancel out all the nonlinearities to make the system behave any way I want. Now I have to sort of think about the subtle nonlinear behavior of my dynamical system and choose carefully my inputs in order to achieve goals. So it turns out for this robot, in fact, you can make it balance up the top pretty easily. This is not really a hard problem for us to solve. And it's not obvious how you might come up with a solution just writing it down on paper, but as we'll see, we can solve problems like this really easily with optimization. Now, you might be thinking, all right, what's this guy on about? He's talking about these really trivial robots and saying, oh, they're missing actuators, and this thing makes it really hard. Why not just put another actuator on your robot arm? Fair enough. In this case, you probably would do that. But imagine I take this robot, I grab it by the elbow, I pull it off the wall. Now we have our simplest model of a walking system. Okay? And what would it mean for me to add an actuator to this to make it not underactuated? Right? That would mean sort of putting an actuator between the foot and the floor so I can make the robot do whatever I want. You could do that, but then your robot's not going to walk very far. Okay? So underactuation is an inherent property of most of the robots we actually care about controlling. Okay? And so what we're going to see is a bunch of much more complicated robots that are underactuated, for which we can no longer solve optimization problems as nicely as we can for these simple systems. Okay, so I'm not here to talk about compensate. I'm here to talk about robots that are more like this. And so I took this slide. This is sort of what it looks like to be a roboticist nowadays. Okay, it's really exciting. And these are not an exhaustive list of the best robots in the world. These are sort of the robots I could find on Google Images that had a white background that made the slide look really nice. But I know a couple of these robots quite well. In fact, I'll talk about this robot here today, is Atlas, built by Boston Dynamics. But what I want to get across to you in the beginning is that hardware is not the problem. Okay? These robots are incredible feats of engineering. They have incredibly strong actuators, super precise sensors. They have inertial measurement units that are the same as what we put in intercontinental ballistic missiles. They've got stereo cameras that can do dense reconstruction of their environment at hundreds of hertz, right? These are incredible machines. So in principle, they should be able to do amazing things, right? They should be able to run at high speeds. They should be able to go over rough terrain or do precise and delicate manipulation. But their physical complexity challenges all of those optimization tools that we use to solve control problems in those simpler systems, right? They don't directly scale up. Okay, so what we can do is take these really impressive robots, and let me show you what the state-of-the-art can do. Right? This is a sort of selective fail reel from the DARPA Robotics Challenge in 2015. And of course, this is showing the worst of what happened at the competition, but it gets the point across that despite the incredible physicality of these systems, the underlying software leaves a lot to be desired. Okay? So one of the themes that I'd love to get across to you is that robustness is the big problem we haven't solved yet in robotics. All of these robots are thinking about themselves as a particular dynamical model. They're not thinking about all the different things that might happen. They're just saying, this is what I think will happen. I'm going to pretend the world exists as just as I planned it. I'm going to execute motions, and then these sort of things happen. Now, this is me. This is not me pointing fingers, by the way. Our robot is in this video, okay? This is our robot, okay? And this is caused by it not predicting that a certain contact was happening on its butt, right? And it fell and it broke its arm. Okay. So here's a question. How should we control computers to, for example, generate stable dynamic locomotion on a robot as complex as Atlas? Well, no spoiler here. Optimization is the tool of choice that we've been using. And so what do these problems look like? Well, they're going to be optimal control problems. All right. So before you recoil, what I want you to do is, if you're comfortable with things like MDPs and that sort of optimization problem, they're exactly sort of corollary to what I'll be writing here. You can change these into sums and change this into max, and it's kind of like your standard dynamic programming type ideas. But this is sort of how controls people like to write this problem. So what is this saying? I want to find some way to generate torques for my robot such that I minimize some cost over time, which could say don't use lots of energy, which could say don't fall on your head, whatever. And if I want to solve this problem, I had better make sure I get a solution out that I can actually run. So I have to think about actually satisfying my nonlinear dynamics. I'm going to be starting in a particular place. As I'm walking from here to the podium, I don't want my head to go through the chalkboard. That's a state constraint. I want to make sure that my inputs that I design actually work through my actuators, input constraints, right? So I can write this whole thing down as a big optimization. And mathematically, what this will be is a non-convex, nonlinear program. Well, people who have thought about convexity and things like this, why is this non-convex? Well, just for example, the dynamics have sines and cosines flying around, so these are clearly not convex functions. But there's lots of choices of how I take this sort of Platonic problem. This isn't real. I haven't really stated things in a way that you can immediately jump on a computer and write it yet. So I can figure out how to transcribe this into a finite NLP that I can actually solve on a computer. I have choices about how descriptive these dynamic equations of motion are, right? What sort of constraints are most important to me, right? You have all kinds of design choices that you have to make before actually instantiating a problem that you can solve. So why is this hard? So many of you have actually solved NLPs before in various contexts. What's the big deal? People solve NLPs with thousands of variables all the time. There's commercial solvers for all these things. Let me try to build your intuition about why these things are hard. So I already mentioned a couple things, right? So we have this underactuation. We have this nonlinearity in our dynamics. We have high dimensionality, right? So this is obviously a high-dimensional system, right? Remember the pendulum had one sort of theta, theta dot. This guy has 68 states, so its state vector is 68 dimensional, and it's got 28 inputs, okay? Its equations of motion live on some sort of nonlinear manifold, and it's underactuated because it's a walking robot. What's more is it has a hybrid dynamics, okay? So what does that mean? Well, if you think about it, as I'm walking around, and I have this foot planted on the ground, I want to walk forward. What's the next thing that happens? I sort of swing this leg forward, and I go boom. My heel hits the ground. So as my right foot was on the ground, I'm sort of this continuous dynamical system like this, right? And I have some constraints that my foot has to stay on the ground and so on. And then my heel hits the ground. There's a discontinuity in my velocity. And then I become a sort of new dynamical system which has one foot and one heel on the ground, right? So I'm sort of different. So that has pretty big ramifications for optimization. First, this discontinuity. What's the first thing you might do when you want to solve an optimization problem? Well, you take gradients, right? Well, if you have discontinuities, that's kind of a problem now. And if you wanted to say, well, that's fine, I'll just solve all of these sort of independent smooth problems and then connect them together. Well, if I do that, I sort of have to know what this enumeration of different dynamical systems is, right? So there's this sort of integerness to the optimization that's imposed by contacts. This is one of the main reasons why solving optimization problems through contact is very hard. Okay, uncertainty. You saw robots that were very not robust to uncertainty, right? They went to reach for a valve and they completely missed and then just fell on their head, right? That's a big deal. I have to solve problems fast enough that I can actually write a controller that runs in real time. And the biggest piece of intuition that I can give to you is that finding something like a stable dynamic walking behavior is a needle in a haystack, right? And that's really hard both for optimization algorithms, right? When you optimize in some non-convex space, if finding a solution is really hard, then it's most likely you're going to get caught in some non-convex constraint blocking you to find a solution, so you won't find anything. And it's certainly hard for learning algorithms. If I just said, here, robot, here's some function approximator to learn how to walk, you're probably going to break your robot before you find a walking gait, right? All right, so today I'd like to talk about two things. One is I want to give you the sort of optimization viewpoint of how pretty much every humanoid robot you've ever seen in your life approaches walking. And I'll talk about the recent work we've been doing that's trying to look at the entire full, complete dynamics of the robot and write down nonlinear programs that we can actually solve to create dynamic motion. All right, so I spent all this time saying this problem is really hard, it's this really complex optimization problem, and you're probably thinking, well, I've seen lots and lots of robots on YouTube or on the Today Show sort of cruising around with no problem. So what's going on with robots like Asimo? So what's going on is they're using these sort of brilliant insights to the fundamental dynamic quantities involved in dynamic balance, okay? So if I had to write out a recipe for Asimo, this is how it works. So first, I'm going to separate the problem of planning contacts with planning smooth dynamic motions, okay? So this is sort of getting rid of the intergenous by just saying, well, I'm going to plan out, throw some footsteps down. That's how I'm going to walk. And then I don't have to worry about all the context stuff anymore. OK, so if somebody tells me when all my footsteps are ahead of time, then I can just do those smooth optimizations in between. And instead of thinking about the entire robot dynamics when I'm doing that, I'm going to reduce the dynamics to something really simple. And we'll talk about what that is exactly. But you might have heard things like zero moment point, center of pressure, these sort of ideas thrown around if you've gotten into robotics at all. So I'll tell you how you get to that in just a couple slides. OK, and then we're just going to use this simple dynamics, and that's what we're going to use to solve optimization problems. All right, so what does it mean to plan the context first? Well, it just means planning footsteps. So here's a video of the approach that we used in the DARPA Robotics Challenge. Well, we just get a bunch of LiDAR returns from the robot's head. So this is just a spinning laser doing time of flight to estimate a volume in the world. We can compute a map of the terrain, and then we can identify automatically regions where you can safely put a foot, and then it'll just throw down some sequence of footsteps in order to get from point A to point B. Okay? The point is not the details of this. I didn't really want to get into this, but I just want to show you sort of roughly what I mean by just throwing down some footsteps and don't worry about all the context stuff and the rest of the optimization problem. What does it mean to simplify the dynamics of something like a humanoid robot? Well, we typically make a couple assumptions. One is that the angular momentum is roughly 0. All right, if you're not comfortable with the idea of angular momentum, just think about as you're walking, you're sort of not like tipping over crazily, right? You're sort of maintaining a roughly 0 angular momentum, and this is borne out by people who have studied this kind of thing in biomechanics. But in the case of the classical humanoid approach, you just set this value to 0 and be done with it. The other thing seems kind of peculiar. It says that the center mass height is roughly constant. I'm not going to tell you why exactly you need that in the math, but it turns out once you make this assumption, things become linear, which is great. Now, incidentally, this center mass height is constant. Now you know that if you learn one thing from this talk, this is what you should learn. That the reason why humanoid robots walk like this is because they're trying to get their center mass height to be a constant, right? So now you can go tell your friends that. All right. So what is this linear dynamics? What does it even mean? So now we're thinking about the robot as a point center of mass and some point on the ground that we're calling the center of pressure. What's the center of pressure? Well, if I'm standing on the ground, I have a bunch of sort of ground reaction forces pushing back on my feet, right? Otherwise, I'd go through the ground. Now, if I sort of integrate those across the bottom of my feet and then do like a weighted average, there's some point which is the center of pressure on the ground. Now, that point is always going to be somewhere below my support polygon, where if I sort of connected my feet with a bunch of edges, like a convex hull. But if it's on the edge, I could be tipping over, right? So that's bad. So if I want a surrogate for dynamic balance, I should just say that this center of pressure, this point on the ground, had better be firmly underneath my foot, not on the edge of my foot. Okay? That's the big idea that all walking robots, or most walking robots you've ever seen, use. Now, the big idea, the cool thing computationally is that I can compute this point on the ground as a linear equation that involves my center of mass, position and velocity, and my center of mass acceleration. Okay? And so I'm going to use y as this center pressure point on the ground. All right? So that's a really big idea. So if I have this idea that I can control balance by just looking at this one point on the ground, and I can compute this point very well by just using this linear equation, right? So that's the big secret. So let me tell you about our sort of optimization view of this problem. So suppose we start with our big robot atlas, lots of complex dynamics and so on. We define some physical mapping, which could be this ZMP center pressure style mapping, which is going to reduce in some result in some reduced dynamical system. Now I'm going to run this trajectory optimization problem. That's that optimal control problem I had on the earlier slide. And then that's going to give me a trajectory. Now I have to control that trajectory using feedback control. So we can solve this problem. I'll tell you what that problem is all about. But what we're going to get out is essentially a value function. Okay? So if any of you thought about MDPs before, you know, computing a value function is equivalent to computing an optimal controller for a state space. So we can do the same thing in continuous time. And so that's what we do. We compute this optimal tracking controller that follows this trajectory. So if my robot's executing the trajectory and someone bumps it, up to some disturbance magnitude, it's just going to go back to the trajectory. All right, then the final piece is that we're going to take this value function for my low-dimensional system, and I need to lift it up so that it can actually run the robot, right? Because this is sort of a controller for this silly little linear system that I just derived by introducing some assumptions. This is going to be the key tool that's going to allow me to take this value function and do something useful with it to control my full robot. Okay. Is everyone with me so far? Let's just stop. Is there anything I've said so far that's not clear? Or are there too many non-clear things that you just can't enumerate them? Feel free to interrupt, please. Okay. So what does the procedure look like? So ignore this equation for right now. So like I said, we're going to lay out some footsteps in space. Now I'm going to define some center of pressure trajectory that goes underneath those footsteps, right? That's going to be my surrogate for dynamic balance. And then I need to compute some kind of a controller that tracks this optimally. How do you do that? Well, there's a thing called the linear quadratic regulator, which is a pretty standard tool from optimal control. And this is exactly an analogous computation as dynamic programming for MDPs. Okay? So in MDPs, we're trying to solve what? The Bellman equation. In continuous systems, you solve something called the Hamilton-Jacobi-Bellman equation. Just some other couple guys' names thrown in there. And it turns out if you have a quadratic cost, this is just saying please stay close to the desired trajectory, please don't use big inputs, subject to linear dynamics, I can actually solve this problem really fast. And in this case, we found that you can solve it as a closed form solution. So ignoring the equations, the takeaway message here is I can not only throw down these footsteps and design center of pressure trajectories for a walking system, I can build optimal controllers in microseconds. Okay? Now that's really cool for a walking system because now, as you'll see in a video later, if I just shove the robot as it's walking, it can instantly recompute new walking behaviors, right? So it's really important for robustness. Okay, so that was sort of quickly through these blocks. What's this whole convex optimization bit about? Well, I said LQR is kind of like this dynamic programming value iteration type idea. So it's going to give me some optimal controller. What do I need to do this other convex optimization fancy business for? Well, the real robot is not this linear system we just arrived at. And in particular, there are important physical constraints that we have to make sure we're satisfying, like friction constraints, like input constraints, right? Like reasoning about all of the degrees of freedom of the robot and making sure that I'm picking physically consistent inputs. Now it's going to turn out this is going to be a quadratic program. Okay. Yeah, I'll just show you what this is really quickly. So if I have our value function in the case of the optimal control problem we talked about, it's going to be a convex quadratic. I just have a bunch of linear constraints which tell me don't violate friction, don't exceed your motor torques, and obey the instantaneous physics of the entire robot, and whatever other things I want to throw in here that happen to be linear. If I want to make sure that I don't put my hand through the table and so on, I can just throw all these kind of constraints in here. And then I can solve a quadratic program. Okay? So if you don't have any experience with convex optimization, by the way, quadratic programs are sort of like epsilon harder than solving a linear system, right? In fact, the main operation inside of most QP solvers is just solving a linear system. You just have to sort of iterate. Okay, so this is like a technology, basically. We know how to solve these problems really well. Okay. Now, if this convex optimization is sitting inside of a control loop that's controlling a robot that's walking, it had better be fast, right? So typical control rates for humanoid robots are something like 500 to 1,000 hertz. So I'd be able to build this QP and solve it at something like 500 to 1,000 hertz. All right, so how do we do that? It turned out we tried some off-the-shelf solvers, Groby, Cplex, CBXGen, and so on. Didn't cut it, so we had to write our own. And in doing so, we just made this simple observation, right, that the active set of inequality constraints in that quadratic program changes very infrequently between consecutive control steps. All right, what does that mean? Well, I had a couple of sets of inequalities. One that had to do with like an approximation of the friction cone. One that had to do with my torque limits. Now, when a constraint is active, it means it's sort of up against the limit, right? So it's sort of at equality. So if I'm railing my actuator, it's sort of at equality, it's at the limit, that's called active. And inactive is when you're somewhere else in the middle. Okay? So if the active-inactive pattern doesn't change rapidly, right, which would probably happen if the robot was vibrating horribly or something like this, then we can exploit that temporal structure in order to solve these QPs really fast. Okay? I'll get into this additional layer of complexity. So it turns out this works really well. And the reason it works really well is essentially 97% of the time, we can just solve a linear system and get the optimal solution to the QP, right? So that's great, because we can solve linear systems really fast. And we're much faster than all these off-the-shelf techniques, so we can solve QP in like 0.6 milliseconds, so it's much faster than we needed, but it was still cool. And in order to see why, here's I don't know if you can see this, but this is Atlas climbing a pile of cinder blocks, and you can plot the active set over time, and you can see that there's these very consistent chunks of activity going forward, and that's exactly the structure that we're exploiting in this algorithm. All right, let's see this in action. So this is Atlas, and here's some initial balancing sort of tests that we did. Here the robot's got sort of a foot on a pallet jack, or sort of jacking it back and forth and moving it, making sure that it's compliant. You're just sort of doing this weird dance sort of thing. And here's a couple of graduate students jumping on the suspension of a utility vehicle while the robot's bouncing on one foot. Incidentally, I think that's probably better than I can do. I don't know that I'd be able to withstand, maybe. All right, I'll just go rapidly through a bunch of videos. So here's the robot scanning the ground, finding a board, planning a motion to go pick it up, picking it up, and then it just sort of puts the board out and drops it. It's like, I call this the loneliest game ever. And this is actually a unit test, right? So how many people have written unit tests for their code? More hands should be up. Come on, you got to write unit tests. This is a physical unit test, right? So on a Friday, you could just run this, and if the robot could find the board and pick it up 5 times in a row, we probably didn't break any of the code that week, okay? Here's an example of walking on just not flat terrain, so over some tilty cinder blocks. Here's a comparison of speed over time. So when we originally got the robot, this is the walking control that was provided to us with it. So it was very, very slow. It was something like 3 centimeters per second or something. It was very slow. And then this here at the bottom is right before the competition last April, and it's walking at about 0.5 meters per second. Now that's certainly slower than I think probably everyone in this room. But when it's a 400-pound hydraulic humanoid robot, it seems really fast. And we think this is basically the physical limit of this robot. So it has a hydraulic pump on board, and so whenever it moves fast, it has to generate a lot of flow in the system in order to maintain pressure. And we were pretty much at the limit of this hydraulic pump. So that's about as fast as Atlas could go. Okay, and here's why we had to solve those optimal control problems really fast, right? So you have jerk robotics engineers come and punch robots all the time, right? And just as it's recovering, we hit it again, right? Now, if I wasn't able to solve those problems that fast, you can't do that. So this is the beauty of the simple model, right? So you can see Atlas is not walking like you or I. It's still got this sort of bent knee style humanoid locomotion. But because we've said, well, I'm going to make those simplifications, and I can be very reactive. Okay, so that's sort of a trade-off we have. And we didn't just do a bunch of in the lab tests. We actually took this to a competition called the DARK Robotics Challenge, which was an international competition. About 20 teams competed, brought amazing robots from all over the world, and the goal was to try to improve the technology of humanoid robots so that they could help humans respond to disasters like Fukushima. And so what do we have to do? We have to have a robot that could drive a utility vehicle and climb out, open doors and walk through them, turn on power drills and cut through walls, walk over cinder blocks, climb stairs and ladders, lots of stuff, all in 1 hour without direct control of a person. And what do I mean by direct control? Well, we had communication with the robot, but over a degraded and delayed network link. Okay, so we couldn't just sit there and like tele-op every joint. Not that we would want to do that anyway. It's not very interesting. So this is really challenging. And we had 2 tries, right? So as you saw, we fell out of the car on one of them. But it ended up being really cool because we broke the arm and then we got back up and we solved the rest of the tasks with 1 arm. And it was not the arm that we had practiced with. But because we're using optimization, optimization doesn't really have a handedness to it, right? It just says, here are the resources available, solve this problem. Okay, so that was sort of a failure turned into a success story, happily. But this is a lot of fun. It certainly raised some issues about what are the important problems we need to solve moving forward. Okay, so let's assume less. Let's see what happens when we start to back off this assumption of I can build a linear system that describes my robot dynamics. Let's say I want to put my angular momentum back in, say my robot could be sort of tipping at points in time and so on. I still want to forget about torque. What you get back is a dynamics. Don't worry about the equations again. You get a dynamics that just relates how external forces change your linear and angular momentum. Okay? So whenever I push on the board, if I push really hard, then I'm going to tip over, right? So that's an external force changing my angular momentum, right? The big takeaway here is I go from a 68-dimensional dynamics down to a 6-dimensional dynamics, right? So now we're nonlinear. We don't have a nice linear equation anymore, but we still have a really much lower dimensional system to optimize over. So when I make that assumption, now we can start to do cooler stuff, right? So here's dynamic jumping in simulation, jumping down from a height of a couple cinder blocks. So this is decidedly not ASIMO-like now, right? Just making these slightly less assumptions, we get to do more things, right? And here's a running gate. As I said, I don't think Atlas could actually execute this gate because of the physical limitations of the robot. But anyway, we still would like to push forward on the algorithmic side. OK, so that's cool. It seemed like that was pretty cheap. We just removed a couple assumptions. Behind the scenes computation got a little hairier, but don't worry about that. We can sort of start to do really cool things. What's the problem? Well, I still had one assumption that I injected in order to get down to a 6-dimensional dynamics. And that was that I didn't care about torque. That's actually a pretty big deal. Why is that a big deal? Because now I can't guarantee that the solutions I get out are actually achievable on the physical robot. And I can't penalize torque, right? I can't say be energetically efficient. In other words, I can't do that trade-off between how much of the passive dynamics I use and how much actuation I use, right? And that's definitely not how animals behave, right? So as I'm walking around, you can see my legs sort of swing like pendula, right? I'm not controlling every single motion of my leg, right? You're exploiting the innate dynamics of the system in order to behave optimally. So I think the problem that we're really trying to solve now is generating reliable and efficient dynamic motion and locomotion for robots. So how do we do that? Let's get rid of this whole physical mapping business, right? I want to take the dynamics of this guy, stick it right into the optimization problems, and see where we can go. So now we're back to this big, hairy problem that this is a sort of caricature of the optimal control problem. Now, as written, this is sort of like an infinite dimensional LP that you can't, NLP that you can't really implement. So we have some decisions about how to actually transcribe this into something that fits in a computer program. So let me tell you one technique for doing that. So suppose I have some system. This is my humanoid, say. And it has some continuous dynamics, and there are trajectories that satisfy these dynamics. Okay, so what I can do is say, I'm just going to approximate this by looking at a finite set of points along the trajectory. And then I'm going to approximate the equations of motion using an iterated map. Right? So this is just sort of Euler integration. So I'm saying instead of having an x dot equals f of x, yada, yada, I'm saying I have a discrete time system now where I'm integrating using some time step parameter h. Okay? Does that make sense? Have people seen this thing before? This is a pretty traditional way to actually implement, or a really simple way to actually implement simulation on a computer. Okay, so given that, now I can actually write down an optimization problem that we can put in a computer program. I could say I have some horizon M, right, where I have a bunch of states that I can visit and a bunch of torques I can command at those times. I'm going to enforce my dynamics up to discretization using a set of nonlinear equality constraints. Okay? And I can put in torque limits and everything, right? Does that make sense? All right, so I'm just saying, you know, here's some trajectory. You can pick anything you want here, but it had better sort of satisfy the dynamics up to the discretization. Okay, so that is a very classical way to write down an optimal control problem. This goes back decades, and lots of people in aerospace use this, for example, to plan trajectories for spaceships and so on. What's missing? Well, remember I made this whole thing about robots going in and out of contact. As I've described it, that was really just for a smooth system. So somehow I have to represent contact in this optimization. So how do people do that? Well, this looks kind of messy, but let me tell you what's going on here. It's really intuitive. So all I'm saying now is I'm going to allow my optimization algorithm to pick what the contact forces are going to be. That seems pretty sketchy, right? It's saying, well, you can decide what the world's going to do back to you as you're moving around. Right? It seems like now I can just make up contact forces that help me achieve my goals, but we're going to constrain them in such a way that they actually reflect what physics will do. Okay, so how do we do that? Well, first we're going to define this function which says how close you are to the ground. So I could say here this phi function is going to be, I don't know, 10 centimeters, and here it's going to be 0. Right? So I have to be above or on the ground. Can't go through the ground. The forces I pick had better satisfy friction. Right? So I'm going to have some friction cone. And then I have this additional thing. This is called the complementarity constraint. And this says that the inner product of this and this have to be 0. So what does that mean? That means that if this is non-zero, if I'm off the ground, then my forces had better be 0. Right? Which makes sense. Now, if this is 0, this can be non-zero, but it still has to obey friction. Right? So this is a very concise way to represent only choosing forces that are physical. Okay? Now, by throwing all this stuff in, now this algorithm can figure out what contacts to make when, which is really cool.
There's no acceleration? It is allowed for acceleration?
OK, so here we're just talking about states which have positions and velocities, and we're in discrete time. So we're multiplying the accelerations that come out of this with a time step to turn them back into velocities. Good question. Any other questions about this? All right. Now, if you have any experience with integration before, you probably said, you sort of cringed a little when I said that we're going to discretize our dynamics in time. There's good reason for that. So the error, right, so the difference between this trajectory and this trajectory increases linearly with the duration of this time step, right? So that's bad. That means I have to pick lots and lots of points here along this trajectory in order for this to have high fidelity, which means my NLP has to get really big, right? That's not so good. And here's an example to give some intuition. So here's our acrobat again. Here I've planned a trajectory. Here it's going to be the open loop trajectory, which we expect is basically going to fail. And then we have a closed loop tracking controller. And then we've increased the number of knot points from 40 to 100. And what you'll see is, although the plan looks to our eye pretty reasonable, none of these succeed, right? Because the integration error is sufficiently high that you put a tracking controller around it, it's just not representing the physical trajectory. All right. What do you want time? All right, I'm going to start going a little fast through these details. So there's another classical approach to dealing with this problem called direct collocation. The idea now is, instead of having a piecewise linear approximation to your trajectory, this is going to be a cubic spline, right? And there's some various constraints that you can implement to enforce that the spline really represents well the underlying dynamic trajectory. And now if I just switch to this type of integration method, things become a lot nicer. So now with just 20 knot points, I can stabilize these trajectories. So what does that mean? That means that my NLP can be a lot smaller if I use this other integration scheme. OK, so the problem is, if I want to now put the contact stuff in, we have these manifold constraints that pop up that kind of ruin DarkonAha for us. Let me explain what that means. So in DarkonAha, I'm saying I have some one knot point. This is x at time t plus 1. And I'm going to interpolate these two states with a spline. Now, if I do that, what's the chance that one of my feet is going to come off the ground or go through the ground in between? Pretty high, right? You can't just interpolate in joint space using a cubic spline and expect that all of your time-varying equality constraints are satisfied, okay? So one thing we did recently is come up with an extension to direct collocation called DarkonAha for constraints, where it basically takes this spline constraint and projects it onto a contact manifold. And we can prove that the integration error is cubic in H, so it's much better error. It's the same as Darkol, but it handles arbitrary manifold constraints. So what's the takeaway from this? So now I want you to think about, these are sort of goofy looking trajectories, but think about what this looks compared to the sort of ZMP style trajectory. Now I've got straight legs, I've got pendulum swinging of the legs. It doesn't quite look human because I haven't told it to look human. I just said minimize energy, right? And here it is climbing a step. And again, it looks ridiculous. But it's minimizing energy. It's clearly minimizing energy. It's sort of like this weird pendulum robot climbing a step, right? And it's got multiple contacts and so on, right? So this is now a tool that allows us to have manageably sized NLPs that also give us high dynamic fidelity for doing this kind of motion. All right, so what's the story so far? The story so far has been that there's this trade-off between simple models in computation and dynamic capabilities, right? So I can say my robot's a linear system, and it's going to walk around like this, but I get to be really reactive and have cheap computation. If I want to throw the entire dynamics into the thing, things become computationally more expensive, but we have some cool tools that allow us to get at least very good accuracy. Now, what we haven't dealt with yet is explicitly is this idea of robustness, right? And robustness was a thing that I sort of said, this is the big deal, right? This is the thing we really want to be able to tackle to avoid this kind of stuff, right? So what do I mean by robustness? It's not just this sort of integration error type thing. It's what if there's wind gusting on my robot as it's walking? It's what if my model that I've built isn't quite right? Or there's significant dynamic effects that I haven't captured in my model? What if my robot walks into a door frame, right? These are all important things. So how do we represent that? Well, we're going to say there's some set of disturbances, capital W, where I can take elements from this set and throw them into my dynamics. And what we're saying here is these can enter in some arbitrary nonlinear way. These could be parameters of the model. They could be forces acting on the exterior of the robot, and so on. We're not really making any assumptions about that. All right. Now, the big difference here is if I care about optimizing motions subject to some set of disturbances, really what I'm saying is I want to optimize how my system will respond when those disturbances occur. Now, it's not sufficient to think about just an open loop trajectory and then worry about controlling it after with LQR. Now we have to plan both the trajectory and the feedback controller all in one, right? Because if I'm going to optimize a cost that involves these W's, then I have to know how my system is going to respond to all kinds of different external disturbances or model errors. Does that make sense to everyone? Okay. So there's lots of different ways you could think about doing this, and there's a whole history of work in robust control. The problem is when it comes to nonlinear systems and complex systems like robots, it doesn't really translate, at least in a computationally reasonable way. So what we've been trying to do is come up with a computationally cheap extension to standard direct optimization techniques. It's going to allow us to optimize robustness. All right, so I've written this cost term that looks pretty funky, and I agree it looks pretty funky. What's this saying? It's saying that I'm going to incur some cost over my trajectory that is, this is saying that basically I have some deviations from my nominal behavior which are caused by the wind gusting, and I have some deviations from my nominal control, which is me reacting to the wind gusting. And I have some costs that's incurred on these. Maybe it's some quadratic cost that says, if you have no deviations, then you're a perfect control system, then there's no cost here. But in general, there's going to be some cost incurred whenever you deviate from your nominal behavior. Okay? Now I'm saying I want to integrate that over all possible disturbances, right? So I have some set W saying everything that could ever happen to you, integrate the cost over this entire set, and then sum it up along the entire trajectory of the behavior. This looks highly intractable, and in general, it definitely is. But But the idea is, let's suppose we can compute this, and then we're just going to add this cost to our optimizations that we've already been talking about, and then we're good to go. So then the question of the day is, how do we, under what conditions can we actually compute this function in a reasonable amount of time? So what we've been looking at is if this set W is ellipsoidal, and we assume that we're still using time varying LQR feedback, then it turns out we have a closed form computation that can give us this cost. And it can also give us sort of the deviations of the state along the trajectory. So now I can impose constraints like, okay, if the wind gusts, it's going to make me shift this far to the side. So therefore, I bet when I walk through a doorway, I better give myself a little extra room. Those sort of things can just fall out of the optimization. And so far in our experience, we found that it's roughly similar to the standard non-robust techniques that everyone's using, right? So the goal is to build a tool that can make robots more robust that people will actually use, because there is this problem of doing lots of theoretical work and then no one actually using it. Okay, so we just have some initial things. We're working on papers for this now. But here's a quad rotor, which was flying through this geometric forest. And here you can see on the red trajectory is what the standard trajectory optimization gives you. And now if I say that there's some random wind gust model, what it's going to do is just sort of give itself more room as it goes through the trees. And similarly here, this is a simple cart pole system that's using a cart back and forth actuator to swing a pendulum up. And it has unmodeled friction acting on the cart. And if I just run regular trajectory optimization, it fails. And with the robust optimization, it does not. OK, so I'm just going to wrap up. I want to just point out a couple things that I didn't talk about at all. Was this really cool flight work that we're doing in the lab. So we're trying to improve the dynamic capabilities of fixed-wing aircraft or nearly fixed-wing aircraft in dynamic regimes such as high angle of attack for perching or flying in and out of contact. These things are, I think, really fun problems. We have a couple papers we're working on or have published on these on a variable sweep wing design. So how to sweep the wings back and forth in a lightweight aircraft and doing trajectory optimization where you don't have to compute derivatives. Remember that thing about Atlas not sort of moving as fast as we wanted it to? So our sort of algorithms were outpacing the physical robot. So we're hoping to fix that now. And so this is the robot that'll be joining our lab in the spring. It's called Cassie, and it's meant to be a really high-speed ostrich-like robot that we can take outside and have it run at full speeds. And one of the problems we're really interested in is how to do perception in the loop locomotion, right? So we've all seen those videos of mountain goats that can just fly up the corners of mountains and quickly pick out footholds based on visual feedback. We want to understand the process that underlies that and try to reproduce it in a robot. Okay, here's a couple other things going on. We're doing some really cool manipulation work in collaboration with MIT and Draper. We're also doing control optimization for soft exosuits. This is more of a machine learning side of our lab in collaboration with Connor Walsh. All right, so I'm happy to take any of your questions. Yes.
How many floating point operations are required for some of these different maneuvers?
Lots. So I mean, it's.
What processor is used?
Oh, so we're just using standard like gaming PCs, things like that. So like an i7 quad core or whatever. So basically, the way these algorithms work is they take a big nonlinear optimization problem and then iteratively say, I'm going to represent my cost as approximately as a quadratic function, and I'm going to linearize my constraints, and then I'm going to solve like a QP, and then I get to a new point, and I keep doing that. So it's a sort of iterative procedure, and it's not known ahead of time how many iterations will be needed or if you'll even find a solution. So it's sort of hard to say exactly how many numbers are. But for the simple optimization, so initially with the physical robot, those optimizations run really fast, sub-millisecond. The last group of optimizations take on the order of 30 seconds. Yes?
Can you summarize your work with machine learning?
Yes, so in this case, what we're doing is using Bayesian optimization to find control parameters. So we have a parameterized control space of these soft exosuits. So the way these work is they have Bowden cables that attach to custom textiles that help people with hip flexion or ankle flexion. And we parameterize a control space, which is a sort of event-based force profile on the suits. And so given that parameterized space, we're trying to minimize metabolic expenditure measured by a VO2 max signal, like a sort of breath measurement device, and which is a really noisy optimization problem. And we also have experimental constraints where people can't walk with the suit for more than like 40 minutes, say. So we're using Bayesian optimization as a sample efficient black box optimizer. We've got some initial results that look really good. Yes?
I'm curious about your sense from observing nature in natural systems. Is it the hardware that's getting optimized, or is it the software that's being optimized? I mean, I know that's sort of a strange question, but what I mean is that could you design a system that would, in a way that allows you to more efficiently control it? I mean,
Absolutely. Yeah, so the way I'd answer that is that nature co-optimizes control systems and physical systems. And in robotics, we rarely do that, although some people are starting to look at it. Most of the time, we'll just purchase a robot or build a robot, and we have some rough idea of what it should look like, and we're limited by various available actuators and so on and so on. And then we have some system, and we say, okay, now how do I control that? It's not like we're somehow simultaneously coming up with control systems and physical devices at the same time, which is clearly what nature's doing. But certainly on both fronts, on the mechanism front and on the control system front, nature is winning. But I think given our hardware, even though it's not as good as nature, there's a lot more space for improvement with the devices that we have, which is why I'm excited as a computer scientist about this. Yes?
A similar follow-up to that, how much of the robustness problems come from the fact that you're working with bipedal robots? Like if you made one that had 4 legs, would a lot of these problems go away?
Yeah, so 4-legged robots are interesting because they have sort of larger basins of static stability, right? You can turn them into a statue and they're roughly pretty stable. Certainly bipedal robots are challenging because the base of support is so small, but they're also really useful in the sense that they're kind of like tall and thin generally, so there's lots of places they can access that a quadrupedal system just couldn't because its sort of footprint's so much larger. But certainly it's true that depending on how you design the system, the resulting control problems for that system will be potentially radically different. And bipedal robots are hard class systems to control, but that's why we like them. Yeah?
It seems like the center of gravity is really high in these robots. They look like they're wearing big backpacks or something. I mean, does that make the problem harder? And why not just lower it around the hips, basically?
So it doesn't necessarily make the problem harder. You could think about it as if you had a broomstick, right? And you put the broomstick on your hand and you went and had to balance it, you could probably do it pretty well. But if you had the broom top on there, it would be easier to some extent, right? Because the top has sort of as inertia, and you could just move the bottom from underneath it. So in some sense, it can make the problem easier. But a lot of these, like having a big backpack, is not designed to change the inertia of the upper body. It's designed because where else can we put this giant battery that we need? So we need to fix battery technology, and then the backpacks go away.
All right. Thank you, Scholar again.
Cool. Thanks.